Can you see the PPT?
Yes, ma'am, I can see.
Okay. Okay. We were discussing about the last chapter of OOP. Okay. So that is object-oriented design methodology. When you are in a process of developing a object-oriented solution for any problem, what are the best practices you are supposed to follow? Okay, that is about this particular chapter. And in the previous class, we have already discussed the comparison of procedural and object-oriented programming language. And for your understanding, you can easily compare C and Java or C or C++ to understand the procedural and object-oriented language in programming. Okay, C is a procedural-oriented programming language, whereas C++ or Java is an object-oriented programming language. And considering the case study of the bank, okay, where there are 3 types of employees who deal with the loan, we have discussed the different steps involved for an object-oriented design. Okay, so we have discussed, I think, all these 12 steps, right? Quickly revising them. First, you need to identify the classes. Classes are nothing but the nouns, okay, loan advisor, bank manager, teller, etc. Then among these classes, you need to identify the common parameters. Okay, that is nothing but the generalization which decides the general class. Okay, that is the second step. After that, you need to start with the simple class. Okay, as an individual, you need to identify the simple class, okay, or the simple object. And once you decide a class, you need to identify the features. That is nothing but the member methods. Okay, so you need to identify the member variables and methods of that particular class. That is step 4A. Then once you decide the properties of the simplest class, identify the remaining classes. Okay, remaining possible classes that could be generated from the case study. Okay, so identify the classes, identify their member variables, identify their methods. Fine. Once this much is done, next you need to identify whether the class is independent of other classes or not, or if there is any dependency between the classes. If the classes or if the features are independent of each other, then you can keep those members as private or protected so that those variables or methods will not be shared with any other classes. Okay. So only if there is any independency between the classes, you can make their data members as private or protected. Then step 7 is the methods in the cases should completely abstract the functionality. You know that, right? Once you decide about a method, then that should be a kind of some functionality you are supposed to do with respect to that particular class. And you need to check if there is any inheritance possible. For example, employees of the bank. If you consider a loan advisor is an employee, right? Is a relationship. Again, teller is an employee. And bank manager is a loan advisor. Okay, it's a kind of that, so that the subclass or the child class can inherit or can use the features of the base class. So when you have some dependency between the classes, and if that dependency is a relationship, then you need to identify the common features which could be shifted to base class. And if there is any additional features to be performed, you can place them, or if there is any specific functionality to be performed by the individual class, you can make it as a child class or a subclass. So step 10 is you need to identify all other relationships like aggregation and association. Fine, has a relationship and uses a relationship. And always when you identify the number of classes for any case study, for any scenario, do not create redundant classes. Okay, try to minimize the number of classes and be very specific so that the class is used for performing a particular task. Okay, simply creating unnecessary classes complicates the process. That is why keep the number of classes in your application under check. Always review your design. Once you make a design, check if there is any possibility of reducing the number of classes, if there is any possibility of simplifying a process, or just check if something has to be improved. It covers all your criteria, etc. and so on. Okay. Next. So best practices of object-oriented design. What are the best practices of object-oriented design? Yes, when we say object-oriented methodology or object-oriented design, first thing that we need to remember is basics of defining a class. Okay, there are some points you are supposed to understand and remember when you are defining a class. Keep all the data members either private or protected. Okay, that means you should not expose data members directly in your class. Okay, do not make it public so that it's freely accessible everywhere. Always protect your data. That is why you need to keep the data members private or protected. The only data members that can be made public are constants. See, the constants will not be changed. Wherever you use it, they remain as constant. That is why whether you expose it or you just protect it doesn't make any difference, right? That is why the constants you can always make public. Okay. The methods of your class should fully abstract the functionality. Unless and until a class is used to define some functionality, you cannot come up with the method for it. Okay. So when you define a method, that should represent the functionality or the behavior of that class. If any new behavior is required for an existing class, expose it only as methods and not as public data members. The behaviors of the class, you have been studying state and behavior of a class, right? State of a class and the behavior of the class, and behavior is nothing but the functionality. So whenever you need to add a functionality to the class, you need to make it as a member. Okay, you need to share with the other classes as a member and not as a public data member. Okay, it should be a method. Sorry, not a member, it should be a method. Next, if your class has only one data member, and check and see if the class is really required or it can be made as a data member in another class. Making one class just for one member is actually an additional burden. Okay, so in case of part of relationship, if your class has just one data member, check if that data member can be moved to a class with which it has a part of relationship. Okay, so that the class can be removed or eliminated. That is a best practice you are supposed to remember while designing a class. Next, relationships and complexity management. Okay. A class should be self-sufficient in functionality as much as possible. That is the first part. That means a class should be written in such a way that if required, it can be used in another software project altogether. Okay, a class should be designed or should be written in such a way that that class could be used in another software project, another project as it is. Okay, so it should be of that particular structure. Do not design it with the intention that I use it only for my software. No, when we design a class employee, that employee class should be used irrespective of the domain, whether it is a bank, whether it is a college, whether it is any other company. Employee class should represent the employee of almost all the domains. Okay, so that is how it should be designed. Next, if two classes are interdependent so much that one cannot function without the other. If there is any such independency that for the existence of one class, the other class should exist, then there may be or there is a defect in the design. Okay, there should not be so much of dependency. Do not partition functionality across multiple classes. Fine. So do not come to a conclusion that when this is a case, like there should not be too much of interdependency. The object should have or shouldn't have a has a or uses a relationship. It's not like that. There should be dependency, of course. Otherwise, has a relationship and uses a relationship doesn't exist. But when one class is not functioning, it doesn't mean that the other class should stop functioning. Okay, that kind of relationship should be avoided. Do not create unnecessary relationship between classes. Okay, do not create unnecessary relationship between classes. When you do this, okay, when you avoid unnecessary relationship, the design will be simple and design will be extensible. Okay. And the last and important point is, do not try to force fit all the object-oriented concepts you know into the design. Fine. See, it is not mandatory that you should use inheritance, you should use polymorphism, all these concepts in your object-oriented design. Not necessary. Yes, there exist so many features, and it's not mandatory for you to use all those concepts into your design. Not necessary. Okay. So these tools which should be used only when there is a need. Okay. Next, avoid writing too many classes for every single functionality of the class. This we have already discussed, right? So too many classes for performing a single functionality is a kind of having redundant classes, which should be avoided in the object-oriented design. Fine. Whenever you are using the classes inside any framework, okay, or if you're creating any built-in libraries, then you need to reuse as many classes from them. Instead of you reinventing it, you recreating those functionalities inside the program you write, if there exists a library, better you always use them. Fine. Next, always review your design before implementation. Okay, the review is required to remove the redundant classes, redundant functionalities, and to assess whether the relationships identified make sense. If there is any change which has to be adopted between the classes, or if there is any extra class which could be removed, then to do that, always reviewing the design once done is important. So that is about the object-oriented concepts, and by the end of the class or by the end of the day, PPTs will be uploaded to your teams. I'm sorry for the delay. Okay, we should have done last week, but due to certain issues we could not upload it. But today, by the end of the day, the PPTs in the PDF form will be uploaded to your teams. Okay. All right, and you're aware of the quiz 1 schedule which you have already got, and for EIC subject the first quiz or quiz 1 is scheduled on October 2nd. That is not this Saturday, next Saturday. Okay, so on that day quiz will be conducted. It's a MCQ based, and the portion for quiz is complete OOP module. Okay, anyway, we have completed the OOP module. This is the end of OOP module, and we'll be starting with this, our second module, that is analysis of algorithms. So the complete OOP is the portion for quiz 1. Any clarification, any doubts? Any doubts? At least say yes or no so that.
No, ma'am.
No, ma'am.
No, ma'am.
All right. Sorry. We'll start with our second module. Okay, this is called as analysis of algorithms. Okay, our second module is analysis of algorithms. You all are aware of this algorithms concepts, right? So in this particular course, okay, that is in this particular modules, we will discuss the concept of algorithms and why analysis of algorithms is important. Sorry, there is a spelling mistake. Okay, why the algorithms are important and how to analyze those algorithms and what are the factors that affect the performance of algorithms. We will discuss that also. Okay, and this particular module also deals with the mechanism to compute the performance. Okay, performance parameters of any algorithm. Okay, and we will discuss some of the simple algorithms commonly used in the development of software applications. You know, searching, sorting, etc. These are all the common algorithms used everywhere, right? So let us discuss few such algorithms in the syllabus. Fine. To start with the introduction. Fine. We all know that we write the algorithm prior to the design. Okay, prior to the design of the program. Fine. It is actually a design method of the program, I can say. Prior to a design, it's out of the track. I should say, prior to writing a program, we come to a concept called algorithm. Okay, the algorithm is used to design the logic of the solution to a problem, and that solution is represented in a particular form in the algorithm. One important thing you should remember is this algorithm is totally machine independent. Okay, directly the algorithm is not dependent on the syntax of C or C++ or Java. It is not having any such syntax. The algorithm or the logic you design in the algorithm could be implemented later on by any programming language by applying its own syntax. Okay, so the algorithm is defined as a formula or set of steps for solving a particular problem. Formula is nothing but the logic, right? The logic is directly related to the mathematical formula or mathematical interpretation. So the step-by-step method of solving a particular problem is called as an algorithm, and it will have a set of formula to solve the problem. Okay, and it has a step-by-step method for solving the problem in a finite amount of time. Okay, with certain steps, finite number of steps and finite number of time, algorithm will be able to come up with a solution to the problem. Okay, now what are the properties of an algorithm? How an algorithm should be? Fine. The first property you can see is input. Okay. You know that every algorithm, or to come up with the logic for any problem, first you should understand what are the inputs to that particular algorithm. Or when you are designing a software or a system, what are the inputs we provide to a system so that your system can apply some formula or come up with the logic and give you some output. Fine. So the input is nothing but the quantities, right, which are given initially before the actual algorithm or actual design begins. Okay, so you know, we can read the number of students, we can read the marks, we can read the number of integers. They are all the inputs we provide to the algorithm, we provide to the system. Similarly, outputs. Okay, how do you know that your algorithm is working fine? You should get the correct output. Okay, without having an output, it's difficult for you to analyze whether your algorithm is working correctly or not. That is why algorithm should have at least one output. Okay, And of course, these outputs have a specified relationship to the input or relation to the inputs. Okay. Now the next one is definiteness. Okay, you need to define finite number of steps which are very clear. Each step clearly gives you what should be done. Okay, so every step is precisely defined. Okay, and what are the actions to be carried out in that particular step must be unambiguously specified. Finiteness. Finiteness is each algorithm or the algorithm must always terminate after a finite number of steps. It should not go to infinite loop. Okay, so it should terminate after a finite number of steps. That is another property of an algorithm. Okay, next, the last one is effectiveness. So the effectiveness is every step in the algorithm should be easy to understand and prove using a pen or pencil. Okay, so I can say you perform certain operations in your algorithm, right? All of these operations to be performed in the algorithm must be sufficiently basic, okay, so that it can be understood or it can be proved by anybody just by working out the logic using paper and pencil. Okay, so the operations you mention should be sufficiently basic. Okay, so that is a concept of effectiveness, and these 5 properties are very, very important for an algorithm. Fine. So look at the example. The algorithm, you have an algorithm to find GCD of 2 integers m and n. You are supposed to write an algorithm to find the greatest common divisor, or in short GCD, for given 2 positive integers m and n. This is a problem statement given to you and you have to write the Euclid's algorithm to solve the same. Okay. So as I said, there are 5 properties. See how many of the properties can be used here while developing an algorithm. Of course, input and output is mandatory for every algorithm, so you should have it. Among that, leaving those 2, what are the other 3, or if you are able to reach out or achieve other 3, you need to check it out. Okay. Now start writing the algorithm for this. All the algorithms we generally write inside begin and end. Okay, begin and end is the beginning of the algorithm and end of the algorithm, and each operation should be inside a step. Okay, input is one step, operation or the logic is another step, output is another step, and so on. Fine. So before you go with the logic, first step is you need to understand what are the inputs to your problem or to your algorithm. So here it is already given 2 positive integers, m and n are the inputs. So it's given in the problem statement. So you directly consider m and n as the inputs. Okay. So read m and n are the inputs. Next, for finding the common or GCD, first what you do is given 2 positive integers. Okay. You need to divide the first number by second number. Okay. For example, here say m is 15 and n is 3. You need to divide 15 by 3 or divide m by n and let r be a reminder. Okay. R be a reminder. So r is equal to m by n. Okay. So what is the remainder? 15 by 3, or remainder is mod here. So 15 mod 3 is 0, right? The remainder is 0. When you divide 15 by 3, remainder is 0. Okay. So when the remainder is 0, if r is 0, then n is the GCD, or 3 is the common greatest divisor of 15, 3. Okay. 3 is a common because remainder is already 0. Otherwise, if the remainder is not 0, for example, I will take 15 and 4. Okay, m is 15 and n is 4. Then 15 mod 4 is not 0, right? 15 mod 4 is 3. Yeah, 15 divided by 4 is 3 and the remainder is 12. 15 minus 12 is 3. So if the remainder is something other than 0, then what you do? Set m is equal to n. Fine. What is the value of n? N is 4. So m will be 4 now and n is r, remainder. Remainder is 3. Okay. So m will be 4 and n is equal to 3 and you go back to the step 2. Again you divide m by n and check what is the remainder and you keep doing this till the remainder is reaching 0. Okay. When the remainder is reaching 0, whatever the value of n is, that will be a GCD. Okay. So this is how you design an algorithm based on the logic. And generally, when you are writing any algorithm or writing any logic, you need to practically trace it, okay, how it works, and then you should come up with a logic. Just by simply seeing a program, one cannot come up with the logic or come up with the algorithm for every solution or for every problem. Of course, the simple ones can be easily done, but the complex ones or the real world application type of problems cannot be solved directly. You need to trace out with certain values and see if it works. Okay. Now, in this algorithm, you know that during every iteration of the algorithm, there are so many iterations, right? You need to divide. After that, you need to check if the remainder is 0. If the remainder is not 0, again you need to set the values, go back to step 2. So executing one set of all the steps, once is one iteration. For the second time you execute them, that is the second iteration. Third time you execute them, it's a third iteration, and so on. So algorithm will get into several iterations to come up with a solution, right? So those many iterations, and in every iteration you can see the value of m and n decreases, right? M is assigned with the value of n and n is assigned with the value of r. So that is always a value getting decremented in every iteration. Okay, and eventually when the remainder reaches 0, the algorithm terminates. You just input the value of n and you come out, right? So after certain number of steps, of course, it comes out, right? So finiteness is achieved here. Yeah, and effectiveness, of course, okay, by default effectiveness will be there, right? So input you clearly specify and every operation is clearly specified in each step. So effectiveness is achieved. So try to incorporate all these properties in the algorithm you design so that anybody will be able to understand your algorithm and accordingly they can implement it as a program in any language they know. Okay. So that is about one algorithm to find the common or GCD of two positive integers. Fine, this is a simple algorithm. We have already done these algorithms in our PSUC class, but just to understand, we are teaching them again. Next, another important topic to remember is a pseudocode. Okay, as I said earlier, algorithm is independent of any language, right? It is not using any syntax of C or C++ or Java. It's purely independent of any language. But the program you write is dependent on the language or dependent on the machine. The program you write in C cannot be executed in a Java compiler. Similarly, the program you write in C++ cannot be executed directly in a C compiler. Okay. So that is why we call it as machine dependent or language dependent. Fine. So the program is machine dependent where algorithm is not depending on any language or machine. It is usually general in nature. Okay. Now the difference or the gap between algorithm and program could be fulfilled using the concept of something called as pseudocode. Okay. Pseudocode is neither an algorithm nor a program. It is in between the algorithm and the program. Okay. But the concept used in the pseudocode is the algorithm. The same logic will be used. And the pseudocode can be migrated into a code in any language. Okay, that is why it is in between the algorithm and the program. Pseudocode is a high-level description of the algorithm. Okay, high-level description of the algorithm, and it is less detailed than program. It is the extension of algorithm. Okay, that means you get the more detailed versions than algorithm in the pseudocode, but it is not a program. Okay, you will not have all the syntax and everything mentioned in the program in your pseudocode. That will not be there. It will not reveal the design issues of the program. It is basically abstract in nature. The design issues with respect to the program cannot be addressed in a pseudocode. Of course, you represent it using English language, and it is a way to represent the step-by-step methods in finding a solution to the given problem. That means, in other words, it's a representation of the algorithm, right? Okay. Now, we have an example for pseudocode. You can see. You can make out the difference between an algorithm and a pseudocode here. Okay. This is a pseudocode. This is not algorithm. This is a pseudocode. Okay. Representation of a pseudocode. Okay. You have the name of the algorithm, array max of a comma n. You can see that we do not provide it as a input. Instead, it is just given as array max of a comma n. It is understood that a comma n are the parameters provided for this particular function or pseudocode. Okay. Now here, input array as a of n integers. You have n integers and array is provided, and the output is you are finding the maximum element of a. Okay. Basically, this is taking the entire array as input and finding the maximum value, the largest value of the array. Fine. You are aware of the logic, right? What we do, we have an array A, one-dimensional array, say of size 10. Whatever I writing is visible to you, right?
Yes, ma'am.
All right. Now I have an array of 10 numbers. Okay. What should be done is you need to initially assume that the first element is the largest. Okay. Then you need to compare this element with the second element. Okay. Again, whichever comes to be the largest will be the large value, and that will be again compared with the third. So initially you can see here current max is a of 0. That is a first element stored in this address. Okay. That is a of 0. So initially I will assume this a of 0 is the maximum element. Then I will run a loop because this element have to be compared with the remaining values, remaining elements of the array. So a of 0 have to be compared with a of 1, a of 2 and so on. That is why I run a for loop from 1. A of 0 is already considered to be the maximum. So comparing that number with itself doesn't make any sense. That is why I should start my loop from 1 to n. Okay. And at any point of time, if you get to know that if a of I is greater than current max, then that particular value will be the maximum value. Okay. Say I have 5 here and I have 10 somewhere here. Okay. And this is a of 0, 5 is a of 0 and 10 is say a of 2. Okay. When I compare this a of 0, 5 with the 10, I get to know that a of 2 is greater than a of 0. Okay. When I come to this particular case where a of 2 or a of I is greater than a of 0, my max will be now a of 2, not a of 0. Okay. And again I start the loop. Okay. Again the loop is started where a of 2 will be compared with a of 3, a of 4 and so on. And when you reach the end of this for loop, when the value of I reaches n, whatever the value this max variable or current max variable holds will be the largest value. Okay. This is basically the pseudocode compared to the algorithm. Of course, it is similar to the algorithm, but a bit more description than algorithm in the pseudocode. In the algorithm, you can simply write that instead of this greater than sign and all, you can simply write comparing a of I with a of j and whichever comes to be the largest. It is like how you speak, you can represent in the algorithm. Okay. Now, what are the different algorithmic constructs available? Okay. You know that our C, whatever we write, the programs in C language, whatever you have written so far, you have different flow of executions, I can say, to be very simple. Okay. One way is we have implemented all the instructions in the algorithm in a sequential way. The second is branching, where you branch using if statement, if else, switch, etc. And you again have something called as iteration, which is nothing but the loops, right? The same concept here, algorithmic constraints. Even when you write the algorithm, you need to identify which construct to use. Do I go with a sequential construct? Do I go with the branching? Do I go with iterational? And so on. Okay. So first algorithmic construct is sequential construct. Fine. Sequential constructs means the steps written in the algorithm will execute in the order they appear in the algorithm. I write step 1, step 2, step 3. Step 2 is executed after step 1. Step 3 is now executed after step 2 and so on. Okay. In the order of their appearance in the algorithm, they will be executed. Okay. So step 1 followed by, step 1 followed by step 2 followed by step 3 and so on. That is sequentially executing the steps. So that is about sequential construct. Fine. So the algorithm example is also given for finding the area of rectangle. Okay. Finding the area of rectangle, it's basically a sequential construct. You provide the input, do some calculation, give the output. Fine. So they are executed in the order they are written in the algorithm. The second construct is selectional construct. You write some selection statements and based on that you decide what part of the algorithm to execute. Okay. So selectional constructs are used to control the flow of statement execution in order to achieve the required result. Look at the example here. Okay, algorithm is written. You read marks 1, marks 2, marks 3. 3 inputs are read. You find the average of 3 marks. Okay. So how do you find the average? Mark 1 plus mark 2 plus mark 3 divided by 3 will give you the average mark. Okay. Next, once you find the average, then you need to identify if the student has passed or not. Okay. So set status as student passed. You find the average and you set the student as student passed. Now you need to check if the average is less than 65 or not. They have kept the cutoff as 65 and the average greater than 65 is student passed and the average less than 65 is student failed. So initially you set the status as student passed, then you check the average. If it is less than 65, you update the status as student failed. For all other averages, if the average is anyway greater than 65, status will be student passed. Now, execution of step 4. Okay, execution of step 4. Anyway, the first part will be executed. The second part to execute depends on the first condition you mentioned, right? If the condition is true, if the average is less than 65, only then this student failed will be set. Otherwise, this set status is equal to student failed will not be executed at all. Okay, so based on the condition, you decide what steps to execute. That is a kind of selectional statement, okay, or selectional constructs. So the calculation of status of a student by finding or by identifying the average mark represents this selectional construct. And the selectional construct is in step number 4. You can clearly see, right? So the execution of this statement, set status is equal to student failed, depends on the value of the average. Only if the value of the average is less than 65, then set status is equal to student failed will be executed. Right? So this display status, this status value depends on the value of the average again, right? If the value or the average is greater than 65, then step 5 will display the status as student passed. Otherwise, student failed. Okay. So this is a kind of selectional constructs. And the third construct, algorithm construct used is iterational constructs. Okay, iterational constructs. So iterational constructs are used in an algorithm when a part of the algorithm is to be executed multiple times depending on the condition. You clearly understand now that is nothing but the concept of loops. Okay. Based on the condition, a part of the program or part of the algorithm will be executed several times. Okay. So for example, see the algorithm for calculating the factorial of a number. Okay, factorial of a number. Here they have taken the count as 10. Okay, so calculating the factorial of number 10. Fine. So what you should do every time, fact is initially 1, 1 into 1, 1 into 1 is 1, into 2, that is 2, 2 into 3, 6, 6 into 4, 24. Like that you keep doing, right? Till the value reaches 10. You're finding the factorial of 10 here. You can see count less than or is equal to 10, right? So every time what happens is you find the factorial. Initially, I assume that the factorial is 1. So finding the factorial of 10 is 1 into 2 into 3 into 4 into 5 till n, that multiplication. So fact is equal to fact into count. Count is initially 1. Count will be incremented into 2, into 3, into 4, into 5. So the previously computed result into the count, and the count will be incremented in every iteration. Okay. Now this fact is equal to fact into count and count is equal to count plus 1 will happen for every value or every count that is being encountered. For example, initially count is 1. You compute the fact and you increment the count. Now count becomes 2. You check if the count is less than or is equal to 10. Yes, count is 2. So again you need to execute step 3 and 4. Count will be incremented. Count becomes 3. Again you check the condition in step number 5. If the condition is true, again you go back to step 3 on 4. And you repeat this till this count is equal to 10. Okay. When it is equal to 10, again you execute. But when this count is greater than 10, you come out of the loop. Now you can see that this step 3 and 4 are executed 10 times. Initially the count is 1 and you are incrementing by 1 and the condition is count less than or is equal to 10. So 1 to 2, 2 to 3, 3 to 4, 4 to 5 and so on till you reach 10. That step 3 and 4 have to be executed. So since this fact and count computation have to be executed 10 times, I cannot write it as 10 different instructions. That is where iterational constructs come into a picture. The common set of instructions will be executed multiple times depending on the condition you write in step 5 for this example. Okay. If the condition is true, go to step 3. After step 3, anyway, it is a sequential. It comes to step 4. It comes to step 5. In step 5, you check for the condition. Again, you execute step 3. Okay. So, the condition acts as a control to decide how many times the part of the algorithm will execute. That decide how many times this fact and count computation have to be executed. Okay. So, while writing the iterational construct, the algorithm designer should be very clear about the control condition to stop the execution. Thus, count less than 10 is a condition which terminates the execution or which terminates the algorithm. If that condition is wrong, your algorithm may run into infinite loop and may not follow the property of the algorithm. Okay. So these three are very important algorithmic constructs. Apart from these three, there is one more construct called as recursive construct. Okay. Can anybody tell me what is the meaning of recursion?
It's calling the function from within the function.
Exactly. Yes, calling a function inside the same function. So this particular concept of recursion is typically implemented in modular programming languages. Okay, it's a kind of function call mechanism. Fine. So the function computed by the algorithm are expressed in terms of itself, I can say, right? So the function calling itself, okay, factorial call function, and inside that function you again call the factorial, but the parameters you need to change. That is why you can see a solution to a problem depends on solutions to smaller instances of same problem. That means when I find factorial 5, it depends on factorial 4. Factorial 4 depends on factorial 3, right? So 5 factorial is equal to, I can write it as 5 into 4 factorial. So factorial function is again calling factorial function. So factorial of 4 is equal to 4 into factorial of 3. Factorial of 3 is equal to 3 into factorial of 2, and so on. Okay, that is a kind of recursive construct which could be used in the algorithm. Look at the algorithm factorial there. Factorial of is a function, sorry, and if the value of n is 1, that is when you start from a larger number, say factorial of 5, 5 into factorial of 4, 4 into factorial of 3, 3 into factorial of 2, 2 into factorial of 1, and factorial of 1 is 1. Okay, so that is why that is a stopping condition. When you are doing a multiplication, you should not reach 0. You know that 0 multiplied to anything will be 0. That is why the loop should terminate at 1, and that will be a base condition, we call it in recursive constructs. Okay, so if n is equal to 1, return 1. Fine, you know this logic, I believe. Factorial of 4 is equal to 4 into 3 into 2 into 1. This entire thing is nothing but fact of 3, right? So 4 into fact of 3. You can see in this function, I am making a call to the factorial function again. But here it is 4, here it is 3. That is, it is n minus 1. So in general, this is n. If this is my n into fact of n minus 1. Okay. That is how you should arrive to a general formula when you are writing the factorial or any other recursive construct. Any doubt so far?
No,
Any
ma'am.
doubt so far? Huh?
No, ma'am. No.
Okay. Okay. Next, life cycle of an algorithm. While writing an algorithm, what are the different stages you need to consider? Okay, there are basically four stages in algorithm. First stage is designing algorithm. Then you write algorithm. You need to test whether the algorithm is right or wrong. Then you need to analyze the algorithm. Analyzing the algorithm is basically to see if it is taking more memory, if it is taking more time, if there is any possibility to reduce that, and so on. Next, designing algorithm is you are identifying input, you are identifying the output, you are identifying the logic, etc. and so on. And basically, there are certain approaches for designing an algorithm, okay, such as divide and conquer approach, greedy approach, dynamic, and so on, okay. You are aware divide and conquer is nothing but dividing a problem into smaller units, right? And use a technique to resolve or solve the smaller units. And once the smaller units are solved, you combine them to get the final solution of a problem, okay. So you have an entire problem, split it into several subsections. Subsections have to be solved individually, then you combine it to get a larger version of it, okay. That is about divide and conquer, and we will be discussing all these later on, okay. Now it's just an introduction, so I will just tell you what are these techniques. Next comes the greedy approach, okay. Greedy approach is a technique which is used to find the optimal solution, okay, the best solution to a given problem, fine. So this also we'll be discussing later. Different approaches of greedy or different techniques of greedy approach we'll be discussing later. Then the third technique comes to be the dynamic programming approach, okay. This is again dividing it into the smaller or the subgroups. Fine. We'll be discussing again about this dynamic programming approach later. Fine. So the sub-problems, when you divide this entire one problem into the smaller sub-problems, they are overlapping in nature, basically in dynamic programming approach. Fine. We will be discussing all these things later on in your syllabus in this particular module. So for designing an algorithm to identify or to come up with the logic, basically these algorithms or these techniques will be used, okay. And using these techniques, one will be able to identify or design the algorithm. Next comes the concept of writing the algorithm, okay. So the algorithms are written using structured programming concepts. Structured programming principles are nothing but we generally write these algorithms using high-level programming language, right? And these high-level programming languages use structured programming principles. That is why, in turn, the algorithms are written using structured programming principles. We do not use any mnemonics or anything to write the algorithms. We write it basically in high-level programming languages, okay? So the algorithms are not written using any programming language syntax. There will not be any syntax used. That is why it is program independent, but you represent it in English, right? High level language. That is about writing a program. The third stage is testing the algorithm. Once you write the algorithm, fine, it should be tested to see if it works for all possible input combinations, okay. When I write a algorithm for factorial of a number, I should check if it works for factorial of all the cases, okay, all the extreme cases, everything have to be checked, okay. So that is about testing the algorithms, and some of the techniques used for generating the output so that it can be the algorithm can be tested are boundary value techniques, okay, the extreme cases, equivalence partitioning, random generation, logic coverage, etc. Fine. So you will not be we will not be discussing about these techniques for generating the input in your syllabus, but just remember that there exists some techniques for generating the inputs, okay. And these inputs are to test the algorithm for all the possible ways or in all the possible ways, okay. The last one and the important one for your module here is analyzing the algorithm, okay. Analyzing the algorithm. Analyzing the algorithms when implemented uses computer's primary memory and CPU for execution. We know we write the algorithm, we test for the inputs, we get to know that the algorithm is working fine, okay. Then we implement the algorithm in any programming language, using any programming language. And when the algorithm is implemented in C or C++ or Java, okay, the program or the algorithm uses computer's memory, right, to hold the program and the data required for it. It uses computer's primary memory and the CPU, central processing unit, to process those inputs. And these are used for execution. And to analyze the problem, okay, or to analyze the algorithm, I can say, there is a need to determine how much time an algorithm takes when implemented and how much space it occupies in primary memory. It is very important to understand that. Okay, what is the memory required and what is the time required to execute the algorithm. Okay, the calculation of space and time is very important, right? Okay, so when the space and time are calculated, time required and space required are calculated, it is basically dependent on the type of computer you are running the algorithms. Okay, on what type of computers you are executing the algorithm, that is also important. And if an algorithm is executed on a standard computer, analysis of computer maps to the number of operations being executed on it. Of course, many of us use a standard computer to execute or to implement the algorithm, and the analysis, the space and time required is basically depending on the number of operations. Okay, how many iterations you have for the execution in your program, and how much time each of these operations take, and how much memory each of these operations instructions take. These are basically used for calculating the space and time. We call it as space complexity and time complexity. We'll be studying each of these in detail in your curriculum. That is the basic of your AOA, analysis of algorithm syllabus. Okay, space complexity and time complexity. What is the minimum time, or which set of input takes the minimum amount of time for execution? What set of inputs takes the worst case and the maximum time for execution, etc. These are all things have to be computed. And is there any way we can reduce the memory taken by the algorithm? Okay, that is how the optimal algorithm is chosen, the best algorithm is chosen. Of course, there exist multiple algorithms for solving one problem, but always we need to solve algorithm using the best algorithm, optimal solution. That is with respect to space and time complexity, and that is how the analysis is made. Okay. Next, steps recommended for analysis. Okay, for performing the analysis of algorithm, there are certain steps identified for analysis. So given an algorithm, any algorithm, you need to determine the kind of operations it is performing. Okay, because in a standard computers, the memory required or the time required are directly mapped to the operations that are being performed. That is why first or the foremost step you're supposed to perform is identify the type of operation, whether it is an arithmetic operation, whether it is an assignment operation, whether it is a procedure execution, and so on. Which operation is being performed in that particular step? It's important to identify. Next, get the data or get the set of data which helps the algorithm to exhibit all kinds of behavior. When you have an algorithm to find or to sort an array, it could be sorted in ascending order, it could be sorted in descending order. Okay, so get the data which is arranged in, which is not arranged in ascending or descending order, so that you can exhibit all the type of behaviors like sorting in ascending as well as sorting in descending. Okay, so get all types of data. And since the information about the computer on which the algorithm is run is not known during the design of algorithm, analysis is carried out in two stages. See, when you write the algorithm, you do not basically think about the algorithm or the system you are running on, right? You do not know what is the implement, or how are you going to implement, or on what machine you are going to implement. You always think that, okay, this is the simplest way, or this is the best way I can write the algorithm, and you design the algorithm. That is why they cannot be analyzed equally. So there are two stages. Analysis is carried out in two stages: priori analysis and posteriori analysis. Okay. So analysis based on is it done before execution, before implementation of the algorithm, or after implementing the algorithm. Based on that, these are classified. Okay. So priori analysis is before implementing the algorithm. You do not know what machine you are running. So you analyze the algorithm. As it is, you analyze the algorithm. Okay. You have not implemented it on any machine. You have not executed it on any machine, but just by looking at the algorithm, you analyze it. Okay. Next, the second stage is that you have identified the target machine, you have implemented your algorithm in the machine. After implementing the algorithm, you identify or you analyze the algorithm. How much does it take? How much time does it take? And how much space does it take? Okay, so that is the second phase of analysis. The first stage of analysis is before implementing. I have say 10 steps in my algorithm. How much of the iterations are happening for each of these steps? Basically, it is a theoretical calculation, theoretical analysis. Whereas the second stage is once you implement it, your system will or your output screen will give you this has taken this much of time, this has taken this much of space. Okay, you introduce some instructions to keep track of the time, to keep track of the space and etc. And that is how you get the analysis. So that is a second stage of analysis, right? And there are certain case studies to discuss in your syllabus. We'll do it in the next class. Any doubt? Any doubt?
No.
All right, if there is no doubt, I will stop the class. We'll continue in the next class. Okay, and